G'day, I'm Ray Tomes from New Zealand. Welcome to this third issue of Saturday Science Summary. We've got a little bit different topic this time. It started with looking at some of the recent news that Explorer 1 has, having left the solar system, gone past the heliopause. It was then picking up a hum in space. And this hum, it's in the range of 1 to 2 kilohertz. So it's in the hearing range, but it varies, and this gives some indication of the density of the material there. The density is a bit higher than they expected. The main thing that happens there is the solar wind is going outwards from the sun up until the heliopause, and that's the point at which the effects of the galaxy take over from the effects of the sun. It's a boundary there, and so Explorer 1 is beyond that boundary. Explorer 2 has yet to reach that boundary. It'll be a few years, I think, yet. So the hum in itself is an interesting cycle telling us something about the conditions. But I got hold of some data relating to the Explorer 1, that its measurements, and it turns out that they are measuring things about the electric and magnetic fields and so on, which are quite interesting in themselves. So I downloaded some of this data and I began to do an analysis of it using the CAT software available from Cycles Research Institute website. Cycles Research Institute is joined with the Foundation for the Study of Cycles now, so it's all one thing. And I'm the science director of the Foundation for the Study of Cycles. So that's why we're doing these things every week, to try and get a bit more scientific stuff out there. And we welcome more scientific people to come forward to give us other information so we can keep these weekly reports up. So what happens when I analyse this? I'm going to put some graphs up to show you some of the things that are happening. Now this is a graph of 1 year of data taken at 1 hourly intervals by Explorer 1, showing the electric field, one component of the electric field that it experiences, and it averages and it sends each 1 hour's data over the course of the year. This is actually before it hits the heliopause. So what we see are, it's got a little bit of fluctuations, and every so often there's a huge spike. Now, I haven't seen any explanation for what those are. It must run into something substantial, and it's all over in a flash in just 1 hour, or maybe it's a blip in the equipment, I don't know. But anyway, those ones do seem, when I did analysis of those, they did show that there was a tendency to repeat after 260 or 520 hours, which is 10.8 or 21.6 days. It's possible that means something, it's possible that it doesn't. So anyway, that was the first thing that showed up. Then what I did, a further analysis, I trimmed those off, because if you have big spikes like that, they will dominate everything in the analysis. So I trimmed those off and brought them down to values near the range of the other ones. And having done that, did a cycles analysis of the fluctuations that are happening in the electric field. A number of periods show up, which are showing in this graph that I've got up here. And ignoring the one of 148.9 minutes, it was near to 160 minutes, 240 minutes, 480 minutes and 720 minutes. Now, these periods are harmonically related to each other. This is something that happens quite often in cycles. We find cycles that are exactly double other ones or exactly triple other ones, or some ratio of 2 and 3, or sometimes other numbers, but a relationship like that. Now, these particular periods have turned up before. I should mention that, so the blue figures are in minutes, the red figures are in hours, and you can see that there's a lot of other red figures I haven't mentioned there. They are all significant at the 5% level. The blue ones, the ones that I've put in blue as well, will be much more very highly significant. We can say these are real cycles. They really exist. The other ones are possibly real, possibly not. But those particular periods that came up there, I have detected those before. In 1995, I was looking at some aspects of the sun. There's some oscillations of the sun that used to be called the 5-minute oscillations, and they've called them some other sort of modes now. They're not exactly 5 minutes, but there's a range of them from about 3 to 11 minutes. There's a lot of different ones, and each of them is due to the sun oscillating in a variety of different checkerboard modes. So what that means is going around the longitude, there's zones, and in latitude there's zones, and it makes a checkerboard pattern. So alternate ones, like the dark squares on the checkerboard, are oscillating upwards while the other ones are going downwards, and then they reverse. And they repeat that about every 5 minutes, depending on which mode. There's a different period, every different mode for the number of repeats around the sun, and the number of repeats in latitude has its own different oscillation period. And when they analyse a long period of the sun, they can get very accurate periods for all of these. I took all these periods and I analysed them together. What I was looking for is there some pattern to these ones that likes to repeat after some amount of time? And I found that there were indeed. And I called these beats in the 5-minute oscillations. And the different beats I've listed at the top of this chart are about 120 something minutes, 240 minutes, 490, 980, 1979, and then below that 82, 164, and above 74, 1484. Those are all going up, multiplying by 2 as we move across to the left, multiplying by 3 as we move upwards. Now this pattern of 2s and 3s, Edward Dewey had found in lots of other things before. This was a new discovery that I made in these beats. The graph at the bottom shows how strong the beats are as we vary the frequency. So we normally talk in terms of frequency for these things rather than periods, and that's in microhertz. And you'll see that there's very big spikes at certain places corresponding to certain frequencies. So those are very real things that are happening in the sun. It's a surprise, really, because these other things are supposedly sort of unrelated, but it turns out through this they're very strongly related. We get these periods, and we see that a number of those periods are rather similar to the ones that we're detecting out here at the outside of the solar system. So I think there's possibly a connection there because it's the sun's still having an influence out there from the solar wind, and if this stuff's going on, it could cause these things to happen in the solar wind. Coming back now to the measurements of Explorer 1, which were only given 1 hour averages. So I could look at the cycles that are above an hour, above 2 hours. It turns out that there are these different peaks in the spectrum, and I'm just showing what the spectrum looks like around some of these periods. So this is in the vicinity of 4 hours or 240 minutes. And you can see there's 4 significant peaks there, slightly different periods. Why there's 4, I can't say, but what that means is when you get a number of periods like that, it means that there's some slight fluctuations in the period that's happening over the course of that year. In the vicinity of 8 hours or 480 minutes. One very strong one there at just a fraction under 8 hours. Again, in the vicinity of 12 hours, we can see some very strong oscillations there. 12 hours, 720 minutes, that's going on there. And then near to 24 hours, or 1,440 minutes. Now, these are all significant cycles that are happening. We may notice that 24 hours, 12 hours is half that, and so on. They are fractions of the Earth's rotation period as well. The question is this somehow something to do with the Earth? I don't think it is, because the data is, Explorer 1 is out of the limits of the solar system, and it's collecting the data, so it's not looking at the Earth. The Earth has very little effect out there. I should mention that when there's a 160-minute period in the sun, and when that was first discovered, it was measured, the Americans measured it, the Russians measured it, it was measured in Antarctica. And originally they thought it's not really in the sun, it's in the Earth, because it seems to be exactly 160 minutes. But as they measured over a long period of time, the phase gradually shifted relative to the day, and they decided, no, it's 160.01 something minutes. That period has been found in many other things. Russian astronomer Kotov has found that period that binary stars like to revolve in multiples of that period, or fractions, that asteroids like to revolve in that the outer planets are on a standing wave that's centered on the sun with an oscillation period of that. So, and black holes at the center of galaxies also relate to this 160 minutes. So it's my opinion that all of these things are connected, that these waves of these periods that we're seeing are ricocheting around the whole universe, particularly from the cores of galaxies and from stars. But it's everywhere, and it's influencing everything. We can find these on the Earth as well, 160 minutes and 80 minutes, the half the period. That one is associated with sleep cycles as well. Humans, they call it a 90-minute sleep cycle, that we come up from dreaming and then come up to dreaming and then go back into deeper sleep again. And it's said to be a 90-minute cycle, but it averages about 84 minutes, so it's quite closely related to these ones here. Okay, I hope you've enjoyed this bit of a tour of the solar system and and other things, and see you again next week, hopefully.